Hello everyone, welcome to today's Knowledge webinar. CloudHPC, a cluster for your CFD FEA simulations. This webinar shows you how you can perform a CFD and FEA analysis using a cloud-based system. The webinar also involves two different applications, FEM analysis of a flange and CFD analysis of an airfoil. So stick around to see this powerful application at work. Today's webinar presenter, Ruggero Poletto, graduated in Aerospace Engineering at the University of Padua, Italy, and completed a PhD in computational fluid dynamics at the University of Manchester in the UK. His work career is specialized in CFD and FEA software with applications that span from motorsport to civil engineering, from energy to turbo machinery. So he's the right person to ask all your questions you might have about the software. I also want to remind you about Knowledge and where you can find CloudHPC on our catalog. And remember, Knowledge is changing the way designers purchase 3D software, offering more choices, more freedom, best advice, and faster service. Check us out at knowledge.com. Now, without further delays, I'm going to share Ruggero's screen.
Yeah. My screen should be up.
Yep, we can see it. Take it away, Ruggero.
Yeah, thanks a lot for the introduction. And I'm very happy to be here with Knowledge and to have the chance to display, to show the capabilities of the CloudHPC. We recently started working together, and thanks to Knowledge, we are pretty sure the CloudHPC can be a great tool to engineers, designers, freelancers, technical designers in simulating and into performing better products. Just a few words about our company. CloudHPC has been developed by CFD FEA Service. We are an Italian company. Our headquarters is in Verona, near the city of Verona. The company has been founded in 2018, and during the COVID period, we started working on the CloudHPC, which has been the first released in 2021. The main business area of the company, I would say there are three main business areas. One is software development, particularly as far as the engineering applications are concerned. One is CloudHPC, and that's what we talk about today. And then obviously using the software we develop and the CloudHPC, we also perform some consulting engineering design activities, in particular locally in the country, in Italy. What is CloudHPC? Well, we probably all know CFD simulation. Well, CFD stands from computational fluid dynamics. I know that you are US based, but Formula One, for example, which is getting more and more popular, is highly based on this type of simulations in order to determine the performances of the car, the drag, the lift, rather than the heat exchange in the motors. So CFD is anything that can be simulated which involves a fluid. On the other hand, there are FEA analysis, where FEA stands for finite element analysis, and it is a different methodology which can be applied in order to simulate structures and consequently find results to static loads, dynamic loads, results on vibrational modes, eigenvalues, frequencies, and everything related to a structure. But obviously analysis or simulations, engineering simulations, can be applied in several other fields. I'm thinking about aeroacoustics, I'm thinking about electromagnetism, I'm thinking also about coupling the simulations together, so running CFD and FEA analysis together to know how the wind applies a force to a structure and how the structure deforms because of that force, and consequently how the wind adapts to the deformed shape of the structure. So engineering simulation can be really a big number, big types, a huge amount of different type of simulations. And in order to perform this type of simulation over the year, the requirements in terms of computing power has become higher and higher. So 20 years ago, we could perform a simulation in a small computer. Now we need, then we needed a workstation, a big one. And nowadays we need an HPC, so a cluster, a network of computer that are working together in order to perform the simulation and to provide us the results of the analysis. Well, what is peculiar about CloudHPC is that you can get access to basically a very high hardware resources and rent it just for use it directly from your browser. Okay, so you don't need to actually purchase a computer, you just can use it for a couple of hours, the amount required for your simulation to produce the results, and then you can proceed with studying and engineering your product. Thanks to this technology, this CloudHPC, what you can get access to the best CFD and FEA software for engineering simulation. Yes, because in our cluster it's dedicated to engineering simulation. So you already find installed, I would say, quite some of the best engineering simulation software you can find available online, on the market, through commercial licenses, and use them straight away to perform your simulations. At the same time, you can get the right hardware to perform correctly and to perform at the best speed the simulations you require the system to make. Okay, remember that the software and the hardware must work together in order to perform the simulation, and the more the software is tuned for the hardware and the hardware is in agreement with the software, the faster is this you can get the result. The shorter is the time it takes you to get the results. So that's what we do. We set up the cluster in the best way in order for you to get the results in the shortest amount of time. Obviously, the platform can be paid, is a pay per use, so it is paid monthly, and it depends on how much you have used the platform over the past month. And at the same time, as soon as you connect to the platform, everything is ready to use, and there's no need, or really a minimal system configuration. There's no need for software installation. There's no need for setup. Everything is ready to use for, is ready up for your simulations. In here, I provide a quick list of the software that are already installed in the platform. I divided them into 2 or 3 categories. The first category is the FEA software, so software dedicated to finite element analysis, so structure analysis. In here, I just represented 3 of these software. The first one is Calculix. This is an open source software which somehow is the open source counterpart of Abacus, more or less. And on the cluster, this has been implemented, it's present in several versions like 2.19, 2.18, 2.21, and under different parallelization method. Generally, any application can be performed in parallel using OpenMPI or OpenMP, or both of them. Well, for Calculix, we have OpenMP, all the versions, and OpenMPI for some of the versions which are specified with the suffix MPI, so you can easily understand which of the Calculix versions installed in the platform are able to perform an OpenMPI simulation. Then there is Codastar. This is a French software dedicated to finite element analysis. It's beautiful because it's a Python library. So if you have some programming skills, that it's a very suitable choice in order to perform structure analysis. And this again is available using OpenMP for all the versions and OpenMPI for some of the versions available on the platform. And then there is OpenRadios. This is another finite element software dedicated to explicit calculation, explicit and implicit calculations. So this is a software particularly suitable for impact analysis, explosions. So very phenomena that have a very quick time evolution history. The second category regards the CFD software installed on the CloudHPC. Well, we have OpenFOAM, which is the most popular software, open source software for CFD simulations. OpenFOAM is available only under the OpenMPI. OpenMP is not implemented under OpenFOAM. Then there is FDS, Fire Dynamic Simulator, a very popular CFD software dedicated to civil engineering applications, in particular fire prevention analysis. CodeSaturn, another CFD software developed in France by EDF, similar to OpenFOAM in terms of functionalities. And then there are numerous other software. In here, I just list some of the most important. SU2, another CFD software for which Salome is a preprocessor which allows to generate, to handle CAD files and generate mesh for engineering analysis. CF Mesh Plus is a commercial mesh generator dedicated for CFD analysis. Energy Plus, this is another software that allows to do energy calculation, energy balances within buildings, in particular big ones like theaters, cinemas, gyms, and stuff like that. SheLab is like MATLAB for data post-processing, TensorFlow for artificial intelligence, ParaView, a post-processors, and the list could go on even more. There are also commercial software installed in the platform. I would like to mention a couple, Siemens, ANSYS. For those, while for the open source software, which I listed before, you can just get on the platform and everything is ready to use. For the commercial software, most of the times, the formula under which we provide them is bring your own license. So you can get a license of the software, you must connect it. That's the only setup you have to do. So connect the license to the CloudHPC, and then you can carry on the simulations. And many others. So I invite you all to get in touch with us or with Novec in order to get information about specific software. Also, because if a software or a version of the software is not present in a platform, we always work together with the users to install their required versions of their required software. So we are quite interactive. It's easy to interact with us. The first thing most of the time I'm asked when describing the CloudHPC is how is the workflow? How can I benefit of CloudHPC? Well, I generally provide this sort of scheme, this sort of workflow, which describes how you work in defining a simulation and analyzing the results of your simulation, and how you divide the work between your computer and the CloudHPC. So on the left, in pink, you can imagine your local computer. So this is the environment where you have your computer and the software installed in your computer. On the right-hand side, in blue, there's the CloudHPC. And obviously in here, there is the internet connections, which links somehow your computer to the cloud HPC. So in general, when you generate a simulation, you start from a CAD file, which must be made in your computer. And then, for example, you can upload this file onto the cloud HPC and use CF Mesh Plus to generate a mesh. Remaining on the cloud HPC, you can move then to OpenFOAM and simulate whatever product you have in mind, that you have, whatever mesh generated earlier with CF Mesh Plus. You obviously need to add the boundary condition and set up the whole simulation, but you can simulate that using OpenFOAM. And then, for example, you can move on and open ParaView in order to post-process the results and evaluate the temperature, pressure, velocities, flow rates, mass flow rates, evaluate your engineering parameters of your simulation. And once you are happy with the results, for example, you can download everything. And if you're a consultant, for example, you can prepare your Word report or document which summarizes all the operation you have done. So in this case, in our computer, we just had to generate a CAD file, and then we perform all the work on the cloud HPC, and then we came back to our computer to perform the final report. Another workflow can be it's just an example. A second workflow could start from a CAD file. We move to the cloud HPC, and for example, we use Blender FDS in order to set up a file dynamic simulator on FDS CFD analysis. Then we move to FDS in order to perform the simulations. And once we are happy, we just download the results of the simulation, and this time we perform the post-processing locally in our computer. That is feasible as well. And then again, if you're a consultant, you can move on and generate a Word or a report or a PDF document of everything you have done. So you see, depending on how you want, you can decide at any time whether you want to do a task locally in your computer or remotely, where you can get access to a massive computer basically. But it depends basically on how the resources required and on the data transfer that you want to transfer basically. A third example is this time using Salome. Basically, again, you start from a CAD file. You can open Salome. You can set up a mesh for structure analysis. Then you perform a CodaStar simulations on Cloud HPC, and then you come back with the results of the simulation into Salome Mecha, and then back again to a report of the results. So again, these are 3 examples. They are not just all the possible workflows that you can set up, but it gives you, it should give you an idea of the possibilities of differentiate the work and let's say ping pong the work between your local computer and the cloud HPC. During the workflow we have just seen, for sure there is a data transfer between your computer and the cloud HPC and the cloud HPC and your computer. Okay, and this data transfer is a communication system that has to be set up between the cloud HPC and your computer, which can work in 2 or 3 different ways. In here, I set up little videos. The first one is using the website. I call it the manual way. You just have to go to the cloud HPC website, log in using the credentials of the application, and once you're logged in, you get a storage environment where you can upload the files onto the cloud HPC, or once the simulation is terminated from the storage, you can download the files from the cloud HPC into your computer. So you can see that as a sort of Google Drive, of Dropbox, a sort of data exchange between your computer and the cloud HPC. Once you have uploaded the file on the cloud HPC, then there is a second page named simulation, which allows you to open OpenFOAM, CFMesh Plus, any of the software we mentioned before, and set up the simulation for OpenFOAM, perform the simulation in OpenFOAM, or set up the simulation in OpenRadios and simulate OpenRadios and stuff like that. Okay, so that's the manual way of dealing with the system. If you are, let's say, a little bit more skilled in terms of programming language, we have a tool named CloudHPC exec. This tool works on Ubuntu, so on Linux under the Ubuntu distribution. And once you install it, it allows you to move the files, execute software, download the files directly from the terminal. In here, we can see on the left-hand side the website of the CloudHPC, and on the right-hand side, I have the terminal of a computer. Now, obviously, we can't see the commands, but typing the commands within this CloudHPC exec package, it is possible to upload files, execute a CFD analysis, and download the simulations results once that is completed. So this, let's say, differently than the manual version, this requires a little bit of programming skills, but it's still, and it only works under Linux. If you are even more under the programming, then we have a full set of API that can be integrated into Python or Bash scripts, and through a list of HTTPS calls allows you to do all the operations we saw in the manual and in the terminal applications, basically. I'm not saying that any of these method is better than the other ones. They are just different methodologies. It depends on which one is more suitable for you. I suggest you to use that methodology. Okay. The main feature, obviously, of the CloudHPC is what we call scalability. So what we want is to perform, for example, an FEA analysis, and we want to reduce the computational time by increasing the hardware size we are using, by increasing the amount of hardware resources we assign for that particular simulation. Because of this, we must be, let's say, aware of the hardware that is installed on the CloudHPC. Currently, May 28th, 2025, the hardware equipped in the platform is the AMD EPYC Milan processors at 3.3 gigahertz, or Intel Xeon Emerald Rapids processors, which are able of 4.0 gigahertz. We are about, but this happens continuously, we are about to integrate also AMD EPYC Turing, which are 4.1 gigahertz in terms of frequency, so a little bit faster than the Intel Xeon Emerald Rapids. And I mean, all this hardware advancement is completely transparent to the users. You just get on the websites and you're using the latest and most modern versions of the hardware. Thanks to this, you can get two types of scalabilities. One is called horizontal scalabilities. Let's say you are a designer and you want to optimize the shape of a chassis of a car. So what you generally do from your CAD, you generate 2 or 3 or 4 or 5 different types of chassis, and you want to apply the loads to all these chassis and evaluate which of these chassis designed is the best one in terms of performances, which can resist the loads applied. Well, in this case, in the CloudHPC, you can submit the simulation of all these chassis simultaneously and run them at the same time. So by the time you finish one of them, you're actually finishing all the 5 or 6 scenarios you have defined at the same time. This is called horizontal scalability. And in our case, every account is able to perform up to 40 scenarios at the same time, 40 simulations at the same time. We have had the request of increasing this limit. Let's say by default, if you this is not available, but if you get in touch with our support, we can give you the possibility also to perform 100 scenarios, maybe for 2 weeks time. Okay, we don't want to misuse the platform, so for this we set this limit, but it's definitely possible to increase this limit to a higher number. And then obviously there is the vertical speed up. The vertical scalability means that I want to simulate a chassis, but a bigger and bigger size. So bigger in size, bigger the mesh size, or even more accurate because I'm reducing the cell size of the mesh. And this is what we call the vertical scalability. And this can be done by allocated more hardware resources on each scenarios we are simulating. Currently, every simulation is kind of limited to 224 virtual CPUs in case you're using hyper-threaded software, or 108 cores in case you're using multi-core, so OpenMPI approaches. This depends on the software you use, which of the two limits can apply. So in theory, you can run up to 40 simulations, and each of these simulations have 180 physical cores. So you can really allocate a huge amount of hardware resources for your analysis. For every simulation, basically, you can differentiate the amount of RAM. Basically, every time you start a new analysis, you are also selecting the hardware where you want the analysis to be performed. You can allocate more RAM, less amount of RAM. You can allocate hyperthread or disable hyperthreaded. Okay, and there are several configurations. Here they are reported. Like you have normal hardware or premium hardware, depending if you want AMD EPYC Milan or you want the Emerald Rapids we saw before, the Intel Emerald Rapids processor, which is about 2 times faster compared to the AMD EPYC Milan. On top of it, we have also a series of tools dedicated to what we call automated workflow. I mean, they don't differentiate much from the workflow we saw before. The only difference is that in these cases, if you use any of the tool we developed internally, you can get a vertical scalability completely performed on the cloud, and that in one click, basically you get a whole turbo machinery simulated. So in Turbo App. In TenuFem is dedicated to gasket analysis. So this is FEA analysis. Valve Flow dedicated to safety valves in particular. BestGate is dedicated to injection molding. EnviFlow stands for environmental flow, so external analysis, thermal comfort on cities, for example. Car parks is dedicated to fire and smoke ventilation of car parks. HVAC flow is thermal comfort in buildings. So we have some of these vertical and automatic workflows available, and users can actually download them from the platform, install them in their PC, and easily perform simulations using these tools. There are some extra tools that can make CloudHPC even easier to work, to use. In particular, the first one is what we call CloudHPC storage. This is a little software that you can optionally install on Windows, and actually makes the storage really like Dropbox, like Google Drive, like OneDrive by Microsoft. So it allows to mount the storage as if it was an external hard drive, and make it easier to transfer the file between your computer and the CloudHPC and vice versa. We have a huge set, a different type, quite a couple of types of connectivity between you and the CloudHPC. The one which is now more popular is the remote desktop. This is available directly in the website, as we're going to see in a little bit in a tutorial, but it is also possible to get a SSH connection to the CloudHPC. So that's up to you. And again, something that we are asked so many times is the support. Yes, this is available. It's available from 9 a.m. to 6 p.m. European time, obviously. We are an Italian-based company. There is a chat. In these screenshots, you can see it. This is the chat for the support that's available online, and this allows you to interact with our support team. Generally, the support are classified into two types. Support for the CloudHPC and the scalability of any software. That is basically unlimited. Instead, the support for the use of open source software, like I'm thinking about CodaStar, for example. If you don't know how to set up a simulation CodaStar, we can give you support and assistance to that. Generally, the amount of hours of support you get is kind of proportional to the amount of times you use the CloudHPC, let's say. Yeah, so now we are going to go to see a couple of examples. The first one is an example I made with FDS, File Dynamics Simulator. This is a CFD analysis of a little staircase. I prepared the CAD file earlier on my own. And then in my computer, I opened Blender FDS and I set up the FDS analysis. Out of this process, I got a file named .fds, staircase.fds, which I'm gonna now upload on the CloudHPC to perform the FDS CFD simulation. I will perform the post-processing online, and then we will download the results. So I'll just go out. This is the CloudHPC platform. Basically, there are two main pages, as we said earlier. Simulations, where you can monitor your running analysis, and storage, where you can transfer the files between your computer and the CloudHPC. In my case, I want to upload the staircase file. So I just press the plus button at the top right. You can see with my mouse, it's right here. I'll just wait for the browser to open the file. Actually, I'll minimize it a little bit. And this is the input file I have prepared earlier. I had prepared it separately before recording this webinar, and I use Blender FDS, but you can use any software. I know there are several commercial softwares dedicated to managing and generating this input file. Some of these software are actually provided also by Novage, so you can also get in touch with them, and actually you can integrate the two softwares together. So to move the software to the cloud is so much easy because it's just a drag and drop. I press save, and the system automatic is going to upload the files on the CloudHPC. This process depends obviously on the bandwidth that your internet connection has available, and usually it's just a matter of a few seconds. So now it's completely opened. I go to the simulation page and I'm ready now to submit the analysis. So I press plus. For every simulation we are going to submit on the CloudHPC, we have to decide the hardware type where we want the simulation to run, the software type that we want to use, and obviously the folder on the storage that we are gonna use for the simulation. So in terms of hardware, this case has been configured to run on a 16 virtual CPU machine with a RAM high CPU. There are several size of RAMs available. So high CPU standard and high MEM, they are different just because of the amount of RAM allocated. Hyper CPU is like high CPU in terms of amount of RAM, but it's a premium hardware. And then we have high core and hyper core, which allocates only physical cores. Under folder, I select the FDS file I had uploaded a minute ago. And under script, I have all the software installed on CloudHPC, and among them, I'm going to select FDS 6.7.5. I just press save, and I'll wait for the CloudHPC to do the rest. So in a second, I'll be redirected to the simulations page, where I can track all the simulations I performed in the past and so that are completed or that I stopped previously, and also those simulations that are running right now. Okay, so I can at any time monitor the simulations that are running right in this moment. At the bottom in here, I have a pop-up that tells me the cost, the hourly fee of this particular configuration in terms of CPU, RAM, and software used. In here, under the simulation page, I can see that I have the simulation that's just been submitted to the system. And obviously, as soon as you submit an analysis, that is going to be impending. But usually after a few seconds, that's going to turn into a new status that's running. And if we just refresh the page, we get into this output a list of operations which are performed by the CloudHPC platform. And these operations generally are preliminary operations just to set up the system, set up the virtual desktop, the remote desktop for you to connect. And once everything is configured, then the simulation starts with the virtual desktop, which allows us to interact with the simulation while this is running. So we'll wait because this setup phase lasts about 2-3 minutes. It's just a fixed time. Yeah, we just have to wait a little bit. Basically, the steps involved in this phase are basically three. The first one is the generation of a virtual machine where the simulation is going to be performed. Yeah, and this is the first step, which has just been computed right now. The second step is the configuration of the virtual machine, in particular installing software, copying files, copying the folder from the storage, and preparing everything for the simulation. And the third step is actually the execution of the simulation. So basically, right now, the configuration of the machine has been completed, and the system is copying the files into the virtual machine. So we just have to wait, I guess, a few more seconds, and this particular analysis is going to start. I'll just have to be patient, but I can already highlight, as you may have already noticed, this output represents a sort of log of operations that are performed by the system on this particular simulation. And this log of operation, one after the other, tells us what it has to do, what it is up to do in order to set up the simulation and to proceed with the analysis. Now it is copying the file, it's providing a confirmation of the content of the folder, and now all the preliminary operations are done. So it's about to start the execution of the simulation. Here it is. If I now refresh the page, I am gonna get the virtual desktop. Sorry, I refreshed it too early. There it is. So right here at the bottom, I have the remote desktop. This is the remote desktop of the virtual machine which is performing the analysis. If you just monitor, it took about 3 minutes to generate this particular virtual machine. And if I just double click on smoke view, this is opening my simulation. This is actually the FDS analysis as it is computed right now. So I don't know how many of you are familiar with FDS, but in here I can for sure evaluate already what has been done into this simulation. Obviously just started, so it hasn't done much, but I can monitor and track the process of this analysis at runtime. If I'm happy, I can just save will render the images, and then I'll find all these images on the remote desktop ready to be downloaded from the CloudHPC onto my computer. So that's one workflow that we have seen together. I'll move back to the presentation. I know there will be much more to say, but in order to provide 2 different examples, I have to be a little bit quick. Yeah, so we saw FDS. The second case that I decided to show you together regards the turbo machinery, a pump in particular. I don't know how many of you are familiar with pumps, but in generally, pumps are made by 2 or 3 components. The first one is the casing, which has this circular shape, and inside of which there is in blue the impeller. The impeller is the main body of the pump, and thanks to the rotation of the impeller, rotation imposed by an external motor, an external engine, this provides the pressure, the head, which is and the flow rate to the pump. Again, every pump has a certain relation between the flow rate, which is displayed along the x-axis, and the head produced. Generally, the higher the flow rate, the lower is the head produced by that pump. So these orange curves represents the relation between the head produced by the pump and the flow rate that allows the pump to work. And in terms of CAD files to generate, there are basically 2 or 3, it's an assembly of 2 or 3 components. One is the diffuser, which is the external casing of the pump and is represented here in red. One is the impeller, we said before, is the rotational part, and one is called the rotating zone. This is an axial symmetric body which must contain completely the impeller. And this rotating zone is needed by the CFD software. In our case, the CFD software is OpenFOAM, to define which volume is under rotation, okay, while everything else is standing still, is not moving at all. And here we have a zoom of the impeller. That's completely within the rotating zone. Everything is also triggered, obviously, by the presence of the impeller, which in the CFD software as a boundary condition must be placed into rotation, but also by the boundary conditions applied at the inlet, here in yellow, and out the outlet, here in purple. So at the outlet, we have one option for velocity, which is a zero gradient for the velocity, and impose a certain pressure for the pressure variable. At the inlet, we have two possibilities. The first one is to impose a given flow rate, and as a consequence to the pressure equation, we just set a zero gradient value. On the other hand, another possibility is to set to impose the pressure and set a zero gradient for the velocity. These two configurations are very useful because if we want to detect the point in which the flow rate is maximum and consequently the head produced by the pump is zero, then we use this second configuration. Instead, all the other configurations can be performed using the first configuration. For this, I use this blue dot for to perform 1, 2, 3, 4 analysis along the curve, and the red dot is used to perform one single analysis at the end, at the maximum flow rate generated by the pump. Well, obviously, OpenFOAM can handle the mesh generation. I don't want to get into the details, but the mesh is composed by inflation layer. There's many things to say. The inflation layer is this extrusion cells from the wall, which is super important in terms of accuracy of shear stress calculations. And obviously we have an internal component which is in rotations, and this component can be managed by modern CFD software into two different ways. One is called multi-reference frame frozen rotor. It means that we run a steady state simulation in which the rotation is modeled by introducing centrifugal force, Coriolis forces, but we don't put the mesh and the geometry in rotation. Okay, so everything is still, we just model the rotation. The second case is to perform a transient analysis in which actually the geometry is placed under rotation. And so we don't model the rotation, we don't take into consideration the centrifugal force because we are actually rotating part of the mesh. Again, in this case, the workflow I decided is, well, first of all, every point I want to calculate along this Q and H chart, Q stands for flow rate and H stands for head chart, becomes a separate simulation. That's why the horizontal scalability is so important, because just to simulate one pump, we need to perform 4 or 5 simulations just to simulate one single pump. Then obviously we take the CAD files, we set up the simulation. In this case in particular, I use a text editor, Vim, in order to set up the simulation. OpenFOAM allows to do that. Other software may have an easier way to set up the simulation. And then I moved everything on the cloud to perform the CFD analysis using OpenFOAM. And we are going to use ParaView to see the results. In this particular case, I go back to the CloudHPC platform. So I go to the simulations, and here it is. I have prepared it earlier for you, this particular analysis, which is in running. I have already launched about 3 or 4 hours ago. And as you can see, I get in the log all the informations about the performing analysis. And obviously I can track, I can open log files like in here, and I can get informations of what actually OpenFOAM is doing. I can monitor forces, torque, or any fluid dynamic quantities that OpenFOAM allows me to track in order to understand the evolution of the simulation, evaluate the absorbed power, evaluate the head generated by the pump, evaluate any sort of data that comes from this particular simulation. And obviously I can use ParaView in the remote desktop. Okay, I open the ParaView. Again, this is a browser, and this is no more my computer. I'm connected to thanks to the browser to a remote computer where the simulation is actually ongoing. And yeah, I can evaluate the pressure. I can color everything according to the velocity. I can proceed further with the analysis, or if I am familiar with the OpenFOAM data structure, obviously the requirements to use the CloudHPC is to know how to use one of the software installed on CloudHPC. In this case, it is OpenFOAM, and under the OpenFOAM data structure, for example, I can easily monitor the evolutions of the forces and the torque calculated at several time steps. Okay, so these are the forces and these are the torques calculated by the CFD solver as the simulation is actually computed, iterations after iterations as the simulation is computed. Yeah, all these operations, as I told you, can be performed remotely. And then once I'm happy, I can just download a CSV file which summarize, I don't know, the Q and H curve of the pump. Okay, so I don't need to download at any time, all the times, the whole set of results produced by the CFD simulation, which can be also massive in terms of dozens of or hundreds of gigas of data. Yeah. So I just resume the presentation. Just give me a second. So we said in this case, obviously, if needed, someone can take advantage of the horizontal scalability and perform all the scenarios at the same time. Let's say more or less all the scenarios, they are different just because the flow rate is different. And we want to simulate it in order to get the head generated by the pump. And then a couple of words about the costs of the CloudHPC. As we said, the platform is 100% pay-per-use. So there are no subscriptions, no fixed cost. Every month, once you register, I'll give you the registration link later. Once you register, if you use the platform on a specific month, at the end of the month, you receive a summary with how much you use the platform. If instead you don't use the platform, there is no charge at all, nothing particular. You can see it like a utility bill that if you're using electrical power, then at the end of the month you receive a bill for the electrical power. If everything is shut down, the resulting bill is €0. The prices are hourly rate, and they depends on the type of virtual CPUs that you're using. They start from 4 euro cent. That's because we are a European company, so all charges are euro. And they go up to 22 euro cent per virtual CPU hour. They depends a little bit on the amount of RAM you are located, the amount of hardware you are located, and on the type of instances you use for your simulation. It's difficult to explain clearly all the differences. I just wanted to give you a range of all the costs. On top of it, something that can happen, costs that are not specified are related to the use of GPU. By default, there are no GPUs allocated to the accounts, but some specific software M-star CFD. I'm just thinking of requires the GPUs to be used efficiently. So in that case, that can be another cost. And then there is the software license. It's an indirect cost because you must purchase or you must have the software license for commercial software and link it to the CloudHPC to use the CloudHPC with commercial software. The last slide of my webinar, and then we leave a few minutes for the questions, is this one with the contacts. And obviously, very important, this is the link for the registrations through the Knowledge portal. And this allows you to register to the platform and test it. That's very important because 300 virtual CPUs are free of charge as soon as you register to the platform. That's everything from me. I don't know if there are questions. I'm open to reply to requests of clarifications or any type of questions that may have come up.
Thank you, Ruggero. That was great. We have no questions so far, but I'm going to switch to my screen to conclude the presentation. And if we get questions, I'll give everybody a couple of minutes to get a chance to ask you anything. So I just want to remind everybody that you can always find Cloud, HPC, and Knowledge. You can go to our webpage and search in the search box, find the product page. Also, you can call us anytime you want. Our phone number is virtually, no, not virtual, really in every page of our website. So easy to find, we'll be there for you. And if you have any questions about compatibilities and products that go well with CloudHPC, we're here for you. Also, I want to remind everybody that this webinar is being recorded and will be uploaded on YouTube later on today. And so you can share it, watch it, and get a better idea of this wonderful set of tools for your simulations. And Ruggero, I don't see questions, so I'm going to thank you first of all. And I want to thank everybody for joining us today. And I want to end it on an invitation to visit Knowledge.com. Knowledge is changing the way designers purchase 3D software, offering more choices, more freedom, best advice, and faster service. Check us out at Knowledge.com. And have a great rest of the day, everybody. Bye, Ruggero.
Thank you. Bye.
Bye-bye.